Hello, everyone. Welcome back to 4DV510. It's been a while since we had our last lecture, and this is actually the last lecture in the course. It's going to be about distance measures. I changed the topic a little bit because I thought this was more interesting, more important to you when it comes to data mining than the topic that we had before. So I'm going to talk to you about distance measures in order to wrap up the course. And well, I just wanted to say thank you for following it all the way here. Thank you for surviving this thing with me in these strange times. And then later I will also record a small video for presenting to you the assignment. And that's it. Basically, then with that, we conclude the course. I mean, of course, we're going to have our exams and everything, but in terms of lectures, we conclude the course content and everything. So yeah, thank you. And let's talk a little bit about distance measures. So, distance measures are something that we have been talking about them actually. Most of the time we're only talking about Euclidean distances, right? But we've been talking about distances in general ever since we started the course, because distance measures or distances between things are very, very important components of most data mining algorithms, right? So when we think about patterns, we think about distances almost inherently, right? So for example, when we talk about clustering, which is, let's say, probably the most common way people usually think about patterns in data, well, we think about groups of points that are similar to each other and at the same time dissimilar to something else, right? That's in another cluster or in another community, for example. So in clusters and communities, they have this in common. The idea is that you're grouping things that are more similar between themselves than they are with other things that are in other clusters of communities. So it doesn't matter whether the data is actually like an Euclidean high dimensional data, for example, or if it's a network. In both cases, we're still thinking about similar and dissimilar items. And for that, we usually use distance measures to compute that. Also, when it's not so clear cut, like for example, when we want to search for low dimensional representations of the data, which is similar to clustering, but not really, because with clustering, we want really, or clusters and communities, we want to draw a line, right? This is inside the cluster and this is outside of the cluster. But when it comes to finding low dimensional representations of data, or let's say summaries of the data, or in any way, any kind of representation of the data that's easier to visualize or to understand, then usually we're looking for new representations that minimize some kind of an error in the representation of pairwise distances. Maybe sometimes we look at all the pairwise distances at the same time with MDS, for example, or PCA. On the other, sometimes we look at local distances more than we look at the faraway distances, but they're still distances, right? Whenever you think of neighbors, for example, any kind of nearest neighbor search or any kind of algorithm that uses nearest neighbors, you're talking about distance, because the way that you compute whether some neighbor is close or not is by using some kind of a distance measure, right? And most of the time, we just kind of assumed that Euclidean was the distance measure that we wanted to use, because it's natural to us to think of Euclidean distances. But we haven't really thought about the Euclidean distance at all. Other distances that are similar to it, and actually we also didn't think about like how about data sets that are not Euclidean, or data sets that are not composed of vectors, where you can actually compute the Euclidean distances, right? And that's what we will do today. And the overall idea that I wanted to leave here was that when you have a distance measure, when you compute distances, whatever came before that doesn't matter too much anymore. It's it's almost like a filter that you apply to your data, so to speak, so that whatever you have in your hand, whether it's Euclidean or non-Euclidean, or it's a network or text or images or whatever, from the point where you computed the pairwise distances between the points, then from then on, almost all data mining algorithms work basically the same. So it doesn't really matter that the data came from a different source, as long as you can compute these distances, and then from that point on, all the pipeline remains the same, right? And that's, I mean, I think the more important power of distance measures. So what is a distance measure? What's the definition of a distance measure? We start by considering a set of points as a space. So we use this terminology, space, right? And a space is any set with any dimensionality, but it's like a place where data comes from, right? So you can think of like if you have a data set with, I don't know, like thousands or 1,000 data points, doesn't matter. You can think that these 1,000 data points, they are a sample of a space, right? The space is larger than the data set. The space is where the data set comes from. So it would be, let's say, possible to sample more data from that space if we wanted, even though sometimes it is possible, sometimes it isn't. But let's assume that this data comes from a space, right? So a space is just like a set of points that come from the same this same, let's say, context, right? For example, two text documents, two text images, or text, two images, two multidimensional vectors, whatever, as long as they come from the same space, right? Because it's, I mean, you can compute distance between two text documents, but I think it would be a little bit harder to compute the distances between a text document and an image, unless the space is set up in a certain way that you're supposed to do that. But if not, then they're coming from two different spaces. So then it's then in that case a bit harder to compute distances between two things. So if we consider that S and Y are 2 points in that space, right? So 2 points that we take from that space, and D is a distance measure defined in that space, then the distance between X and Y is represented as a real number. And that's the cool thing, I think, about distances, and that's what makes them so interchangeable in a way, because you see the formula here. So D is a function that takes the product of S with S. So that just means it's just a mathematical terminology to say that the input is 2 points from the same space. So like two points that arise from the combination of this space with itself. So it could be any 2 points from that space. That's all that it means when you see this SXS. And the output of that function is a real number. And that's the interesting thing, because it doesn't matter if it's 2 documents or 2 images or 2 whatever, the output will always be a real number. And as soon as you get the output as a real number, then every data mining algorithm can work based on that without really caring where the distance came from in the first place, because it's just a distance, it's a value. And I mean, okay, you're telling me that the distance is, I don't know, 0.5, then okay, I don't care if this distance comes from documents or images or vectors or networks or network nodes. It's a real number, and that's all I need to know. And then I will work with this and do whatever else, like clustering or whatever. So however, it's not really that simple, because you cannot just it's not just any function that takes 2 points from space and output one real number is a distance measure. Okay, you cannot just say, oh, just because I'm taking 2 points and outputting one, that means I'm a distance measure. No, there are some restrictions on what can be considered as a distance measure. And these restrictions, I mean, if the function respects those restrictions, then it can be considered a distance measure, and it can be used interchangeably in the data mining pipeline. So first of all, there are no negative distances. So a distance measure never outputs a negative number. It's always either 0 or larger than 0. 0 is also a special value, because if you say, well, this is called a coincidence axiom. So if you say that the distance between X and Y is 0, then you assume that X is equal to Y. So it's the same point. The only 0 distance should be between a point and itself. You shouldn't have like 2 different points and then the distance is 0, because that will be kind of strange, and that will break these axioms. So that will consequently breaks like what the data mining algorithms are expecting from this distance measure. Distances are symmetric. So the distance between x and y is the same as the distance between y and x, which is kind of like how it works in the real world, right? I mean, if I'm far away from someone, then someone is far away from me in the exact same amount, let's say, or distance. And in any distance measure that we define, no matter the input space, should also reflect that. So that's, for example, why if you take a graph that is directed, so the edges only go one way, then usually that is not like the distances in that graph are not actually a distance metric, because usually you cannot respect this symmetry in a directed graph. You can in an undirected graph where the edges go both ways, right? So if A is connected to B, then B is also connected to A. But otherwise, then it's a problem, because, for example, if you have two nodes and A is connected to B, then you can say there is a distance between A and B, but the distance between B and A is infinite, because you can never get back to A from B, because there is no edge that goes back to it. Let's say in the simplest possible a graph with just two nodes and one edge, right? So for example, that example by itself just breaks this symmetry, so it can't be considered a distance. The distance in the graph cannot be considered a distance for directed graphs in general. And the fourth is that distances respect the triangle inequality. This is the hardest one to actually verify. You know, the other three ones are more or less kind of straightforward. When you take a distance measure, you kind of can analyze this in a straightforward way. But the fourth one is a little bit harder. So the triangle inequality basically states that if you have some distance between 2 points, x and y, so you could never have another point, z, such that if I go from x to z and then from z to y, that detour that I just took, that is actually shorter than the direct distance between x and y. That could never happen for a distance measure. Okay, you could never take like a detour through some other point in the space, and that detour would actually end up being shorter than the distance between x and y. If that happens, this is not a distance measure anymore. Okay, and this can happen, for example, again with networks, if you have weights in the edges, right? So for example, you can have a node A connected to a node B, and you can put a weight in that edge, right? Like, I don't know, 5. And basically what you're seeing is that the distance between A and B is 5, right? This edge has this value of 5. So I don't know, maybe this is like distance between two cities, and the road that takes you to that city is, I don't know, 5. Well, let's say 50 kilometers. Let's say 50. And then maybe you have another city that has like better roads, or if it's faster, or for some reason the road between A and B goes through some kind of I don't know, weird mountains area or something like that. And then what happens is that you end up taking too much time. But there's another detour, there's a shortcut through another city that if you, maybe the distance between A and like C, another city C, is 10 kilometers, and from C to B is 20 kilometers. So if you actually go to C and then to B, the total is 30 kilometers. That can happen in a graph. Okay, and it can actually happen in real life, because in real life, roads don't go straight, right? So since roads don't go straight, then you can have shortcuts and things like that. And then it wouldn't be a distance measure anymore. In those cases, we call these things actually dissimilarity measures, in order to separate them from distances, right? So when I talk about dissimilarity, I'm saying I've got a measure of how dissimilar two things are, but I can't guarantee for sure that this measure respects the axioms in order to be a distance measure, right? So then in order to differentiate, we call it dissimilarity. and it's dissimilarity, not similarity, because it's how different they are, not how close they are. But we're going to talk a little bit more about that as we go. But it's just important to know that for a distance measure to be a distance measure, these axioms must be respected. However, there are very useful dissimilarity functions also, and we are actually going to discuss them today also. They are not perfect, but they are useful, and we still use them from time to time when we don't have another option, or simply when that's what we get from our data, especially in networks, because in networks what you get is actually the data, the connections between points, and not the points themselves are usually not that important. The connections between the points are more important. So then we use that in order to extract our dissimilarities, and that's what we have. So we have to use that, and they're still useful. So we still use them, although we cannot call them distance measures. And of course, we're going to start with the Euclidean distance, right? Because it's the most natural to us. It's the one that it's the concept that we think of as distance when we're thinking about the world outside of data mining or machine learning. And when you say, oh, the distance from here to there, it's something that is let's say, the straight line between 2 points, right? Especially when we're talking about 2 or 3 dimensional spaces, because this is what we use in our everyday lives, right? We usually talk about 2 dimensions or 3 dimensions. And of course, we can never be like perfectly 2-dimensional, but I mean, of course, if you're in the ground or if you're in a flat surface, that is close enough to 2 dimensions that you can actually consider that as being a 2-dimensional distance. So, but it's usually at 2 or 3 dimensions. And so this is the natural distance measure, and how the way to compute it is in this formula over here. Oh, sorry. Is in this formula over here. So basically the distance, the Euclidean distance between 2 points x and y, you take that by taking every component of those vectors. So for example, if it's 2 dimensions, then you have 2 components per vector, right? So you will have x1 minus y1 and x2 minus y2. So you take that, you square that, then you sum everything, and then you take the square root at the end. After you've done everything, you take the square root. That will give you the actual distance. And as you can see, I'm using n here, and that's because actually the exact same distance function that we have for 2 and 3 dimensions can be computed for any space. And I guess by now this is familiar to you, because we've used this many times throughout the course, and you've done this also elsewhere in machine learning and so on. So by now I'm assuming that you're familiar with this, right? And that you and with the concept that you can actually take a vector from any dimensionality and compute the exact same distance between them in the exact same way as you do with 2 or 3 dimensions. So just take all the components, each by one, like as if you align the vectors right on top of each other. Then you go and you take each, let's say, item, the first one from both vectors, the second one from both vectors, the third one, and so on. That's what this summation here is describing. So one minus let's say the first element from one vector minus the first element from the second one, that gives you a number, this one, and then you square that. Then you do that for everyone, sum everything, then take the square root, period, right? And all the described axioms are true actually for Euclidean distance, obviously, because I mean, this is the distance, right? This is the baseline as that we consider as being distance. So yeah, the Euclidean distance respects all the axioms. And you can well, I guess the first 3 are very obvious, but for the triangle inequality, you can just think actually about triangles, because that's where the name comes from. So you can think about a triangle that is like 3 points. The idea here is 3 points. So it's you have 2 points and you have a line between them, then you add another point and you make a triangle. So you can reason about it, and you can see that there will never be a triangle where you can actually like take this detour, and that will have a shorter distance than actually going through that. The shortest distance between 2 points is a straight line between them, and that's actually pretty much true. In the worst case, if the third point lies exactly in the line between the 2 original points, then the distance will be the same, right? The distance from A to C, let's say, and then from C to B will be the same as from A to B, because you're just stopping in the middle and then continuing. But it will never be less than that. And that's what you should always think about when you're thinking about triangle inequality. Just use this triangle abstraction. Now, what you may not really know maybe is that the Euclidean distance is actually part of a family of distances that is parameterized. So the Euclidean distance is known as the L2 norm. So it's the two, it's like, let's say it's the member of the family that has the index 2, but there are others. Actually, you could have any with any number, L1, L2, L3, and also L0 or L infinity. These are all perfectly reasonable distance measures with their own quirks and their own characteristics, but they are, I mean, they're reasonable. And the reason why we call it the L2 norm, and so this norm part comes from the fact that actually when you think about the distance between two vectors, be them whatever dimensions they are, and you can think of this distance, Euclidean distance, as being the norm of the vector q minus p. So if you have the distance, I'm using q minus p here just to match the the numbers in the letters in the figure. So if you think of the distance between q and p, which are two vectors, this is the same as the norm of the vector q minus p. So when you do q minus p, you get a vector. That's the vector that is 1 minus, that's vector operations, right? You have two vectors and you subtract them or you sum them, you get another vector. And that's the vector q minus p. It's one vector. Then if you take the norm of that vector, and I guess you guys know a little bit of linear algebra to know that a norm basically means like it's the length of the vector, right? So when you take the norm of that, you have the Euclidean distance between 2 points. That's basically it, right? And that's why it's called a norm. I guess you're familiar with the concept of norms of vectors, so that's why I'm talking about this in this way. And yeah, and the L2 part comes from the fact that it's a member of a family with LR, with R equals 2, right? And the figure here is just to so you guys can have this kind of a geometric understanding or intuition about the Euclidean distance. So you have a point P, a point Q. Then this here, this vector here is the vector Q minus P, right? Or P minus Q. It doesn't matter because it's just the norm will be the same. I mean, the vector is not the same, but the norm will be the same. And yeah, and this is the distance. One way to write the same thing that we wrote in the previous slide is that the distance squared equals the sum of the squares of the individual distances of each component. And the square root here, just for the fact that if you want to eliminate this square here, then you apply the square root to both sides, and then you end up with a square root here. So that's exactly the same. Just a way to write this without a square root. And of course, the individual components that you're computing, they are like the distance among one axis and the distance in the other axis, and with 90-degree angle here. But I mean, just a geometric intuition. But yeah, you do have other distances in the same family. So for example, the L1 distance is what we call the Manhattan distance. And or some people call it the taxi cab distance, which is basically the same idea, because the L1 norm is actually a distance over a grid. So suppose that you cannot go straight to a point because the points are lying in a grid, and that the space between the points, like in the diagonal of the grids, it's not available. Like for example, when you're in a car and you need to go from one point to the other, then you have to navigate the grid of the city, right? That's the distance to you. Like, it doesn't matter to you that a point A is at some distance to B in a straight line, because that straight line will not really, you will not use that straight line when you're in a car, right? You will actually have to go through the grid. So, and that's why it's called like Manhattan distance, because it's the distance that you would go through the streets of a city like Manhattan. I don't know why they chose Manhattan as a city. Maybe someone was working there at the time. I don't know. I'm not sure. So, but basically that's it. The L1 distance is the distance in the grid, and you can see here that if you replace R with 1, so that becomes L1, and then you have the sum of the individual components to the power of 1, which is basically the same as nothing. So it's just you're just taking the subtraction the individual components, then summing them all, and then again you have 1 over 1, which is also 1. So basically the powers here, both this one and this one, they go away. So you end up with just the sum of the differences in each component, which is exactly what you see in a grid, right? So for example, well, in this case, it's a lot of different components here, but if you were going, let's say I was going from point B to this point over here in this corner here, then basically that would be the sum in one direction plus, or sorry, the distance in one direction plus the distance in the other direction. So basically like this and then like this, and that's it. That's what you would get as the distance between these 2 points. In you see that's a little bit different than the Euclidean distance, because the Euclidean distance would actually be the distance in the diagonal of these, let's say, or the hypotenuse of the triangle. And sometimes it's useful. You'll see this a lot in machine learning. I put a link over here, down here, where I got these 2 pictures from. And this link here actually talks a little bit about the uses of these different, well, L1 distances and also L infinite distances. So you can check this later. But yeah, there are actually some uses in machine learning, like ridge regression, which I don't have time to talk about today, but still it's interesting to take a look if you're curious. And then also the L infinite distance, which is quite interesting, because if you think, okay, what happens here if I take R and I just keep increasing it, increasing without a boundary? So 1,000, 2,000, 1 million, doesn't matter. What will happen? Well, what will happen here is that, in a way, every component distance is actually also going to be, let's say, moving towards infinity, right? And when you compare infinities, although that's completely crazy, you can actually do that in calculus and stuff. So what happens is usually that you consider that the largest one is the largest infinity at the end as you move towards infinity. That's kind of a very popular, it's very general way of describing it. But the idea is that if all components, if all distances between all components are being blown up to infinity, the largest one will win. Okay, so the largest one will be the distance that will, let's say, overtake the rest of the distances of the rest of the components of the vectors, no matter how many you have. So at the end, the fact that you have other distances that are smaller than this one won't matter, because they're all blowing up to infinity. So infinity against infinity, the largest infinity wins, whatever that means, which is kind of crazy, but that's how it is in math. So it's just a maximum distance, component-wise distance for all dimensions. So you just take, if you take each one, which is the largest one, like the first one or the second one or the third one, and then that one, you just take that, the absolute value, of course, because it shouldn't be negative. It's never negative, right? So it's always the absolute value, and that's the distance you consider between the 2 points, right? And this also has applications in machine learning, which you can check in this link, because I don't have time to discuss that. And here is just an idea of the shape of the norms of these vectors, or as you change. In this case, they're calling it P, not L, not R, because R is from the book, and the page they call it LP. So, which is, like, I guess, more common actually than the book version. But anyway, it's L something. And you can see that the circle matches what we think. Oh, so yeah, just so you understand what this picture is showing is what is like all vectors that have the same distance equals to 1. So if I take all the distances in 2D that are equal to 1, like from the origin here, this is the shape that they form, right? So in this case, for example, is a circle because every point on the surface or like on the surface or on the circumference of this circle here, all of them have distance equal to exactly 1 to the origin, right? If you can see that very straightforward, that whatever point if you sample random points here, they all have the same distance, which is 1, or the same norm in a way, because that's the length of the vectors. And it's interesting to see, for example, for the Manhattan distance or the L1 norm, that you have a line here where every point has the same distance. So that's kind of strange, right? Because if I basically, like, if I take a point over here and I compute the distance to the origin here, that distance will be 1 according to the L1 norm. But it feels to me like, well, obviously, at least graphically speaking, in 2 dimensions, this vector is smaller than this vector here, right? So for example, if I go straight up, this vector also has distance 1 according to the L1 norm. So that's kind of interesting that different vectors will have the same norm. And that might sound completely crazy, but there are actually specific applications where that is desirable. So you want that for specific reasons. And for example, if you do the L3 norm, where basically you take all these component-wise distances and you make them to the power of 3, and then you take the cube root of that. So you can see that, it changes the powers here, both this one and that one. So it's to the 3rd power and then the cube root instead of to the 2nd power, and then take the square root. And then you can see that it gets a little bit deformed towards the corners, right? So again, in the opposite way as we saw here, what you'll see here is that a vector that goes from the origin to the middle here, it looks, it looks a bit, it does look a bit larger than the vectors like this one or this one, for example, at least in our geometrical definition here of what it means to be larger in 2D, right? And then if you keep going towards infinity, so to speak, in this case, for example, it's a 100, but it's just like at some point here, this doesn't change too much anymore, even after 100. Then you can see that it becomes almost like a square, right? So it's just a very extreme deformation, let's say, of this one, for example, that's pushing towards the corner, so that in this case, a vector that goes from the origin to the corner of the square here has the same norm as the one that goes from here to here. For whatever reasons, this is also sometimes useful. But anyway, I will let you guys go forward with this. Okay, so now we're going to talk about the cosine or the angular distance. They're not exactly the same, but very similar. Which is something that I've already kind of mentioned a little bit through the course. And it is useful when you may be more interested in the direction of the vector than in its magnitude, right? So you don't want to distinguish between a vector and its multiples. And basically, it's something like, it's very connected to linear algebra, right? So linear, for example, when 2 vectors are linearly dependent or independent or collinear, let's say, in this case, not really linear independent because that will be something else. But in this case, it's about collinearity. So how close to collinear they are in a way, which is, well, let's say you have a vector, for example, you have a 2D vector, and that 2D vector has a certain value for the first component, and the second component is 2 times the first one, let's say. So let's say it's 1 and 2. This is your 2D vector. Now you take another 2D vector, and that another 2D vector is like 2, 4. So again, the second component is 2 times the first one, right? So 2, 4. But it's the whole thing, the whole vector is actually 2 times the first one also, right? So it's a multiple of the first vector. And sometimes you're not interested in that because they are basically the same. They're giving you the same information. What do you mean that they're giving you the same information? Well, depends on what your original vectors are representing, right? So for example, I mentioned this in text mining, regarding text mining. Why would that make sense regarding text mining? Well, Think about it. You have a text, and let's say you have a vector space model representation where you take different terms from the text and you count them, right? So you're interested in comparing vector or texts, the vector representations of the texts, as in like, do these text two different text documents, for example, talk about the same thing? So do they actually have the same vectors in a comparable, and this is a good, this is an important word, a comparable way. So for example, if the first vector talks twice more about football than it does about basketball. So again, we can have, you know, that idea where the first element is 1 and the second element is 2. So in a way, if that means frequency, you could think of, well, okay, the word football appears twice and the word basketball appears once. So it talks, so to speak, twice more about football than it does about basketball. And then you have another vector, another that comes from another text document where they talk about football 10 times and about, or 10 times, and about basketball 5 times. So again, they're talking twice more about football than they are talking about basketball. So maybe for you, you want to say, okay, these two guys are very similar because relatively speaking, between the terms, they are talking more or less about the same thing in a comparable way, twice more about football than about basketball. And if that is important to you, then you need to use the cosine distance, because if you take these other document that was like that talked about basketball 5 times and about football 10 times, and you just compute the Euclidean distance to the first one that was just talking about football twice and about basketball once, if you do that, they're going to be very, very far away from each other because the magnitudes of the components are completely different, right? And again, if you think about this idea that the Euclidean distance is the norm between Q minus P, then you can see that Q minus P will give you a very large vector, right? And so the hypotenuse of this triangle will be very, very long. And you don't want that. You actually want them to be, in this case, coinciding. But let's say that won't happen so much. So it's like you want them to be at least very, very close to each other. And this is one very common example of the application of the cosine distance or the angular distance, because in this case, we're not talking about anymore the norm of the vector between these 2 points, but actually the angle between them. And as you can see, since these 2 points are collinear, obviously the angle between them is the same. So you could say that the distance is 0, right? And here we'll have a little bit of a problem with the coincidence axiom, but let's discuss this in more details in the next slide. So, but basically it's this, the cosine or the angular distance basically says, okay, I'm not interested in the magnitude of the vectors anymore. All I'm interested is in their angle. Okay, so if another vector came that I took from another document was talking about, let's say, basketball 30 times and about football 2 times, then that is obviously very different from the previous 2 vectors that I talked about, because they are talking about basketball 15 times more than football. So the angle will be completely different to another direction completely. Okay. And that's what we want to have in this case. Yeah, and we start discussing this by talking about an actual cosine similarity and not dissimilarity or this distance. So we start with the similarity. Like, what's the difference, right, between the distance and the similarity? Well, a similarity is larger when things are more similar or closer to each other. So it's the opposite of a distance. The distance is larger when things are far away from each other, right? And the similarity is larger when things are close to each other. So they're basically just, one is the inverse of the other. So we start talking about the similarity, and the similarity in this case could be simpler, right? We just take the actual cosine of the angle between 2 vectors, right? And to compute the angle between 2 vectors is very easy. It's this is the formula. All you need is just the actual 2 vectors. So you just make a dot product between them and divide that by the product of their norms. And in this case, I'm talking about the L2 norm because it's just the norm of a vector. So that's, I mean, in this case, we're not really talking about Euclidean distance. It's just the vector norm. So yeah, so this it's if you have the two vectors, then all you have to do is just take a dot product and then divide that by the norm of x times the norm of y. That's it. You have your cosine and you have your similarity, right? So this will be larger for vectors that are actually going in the exact in very similar directions. And it will be, and the interesting thing here is that it will be zero, not for vectors that are very far away from each other, but actually for vectors that are orthogonal. And that's because it's kind of like how we understand, for example, correlation, right? So we consider that two orthogonal vectors are completely uncorrelated. But it goes to one in this case, or sorry, for to minus one on the other hand, for opposite vectors. So if you have one vector going in one direction and the other one is going the exact same direction but opposite, that will be minus one. It's like when you're when two things are negatively correlated, right? Instead of not correlated. So yeah, it's a little bit like there's this kind of unique characteristic to this that's related to the actual correlation between the vectors that is given by the cosine of the angle. And so this is similarity, right? It's for minus one, it's very bad because it's a low value. So these two things are going in completely opposite directions. Then it's zero when they're basically just uncorrelated, so they're going in different directions but not opposite, right? So it's different. It's a different thing to be opposite and to be different, right? And then it's one for actually two vectors that are going in the exact same direction with whatever magnitude. The magnitude here doesn't matter. So you define the similarity. You can compute similarities. This has nothing to do with distance, has nothing to do with the axioms or anything like that. And then you can say, okay, so if in that case, it's easy, right? I can just take the similarity and compute the cosine distance or the cosine dissimilarity. Again, we're going to discuss that simply as one minus the similarity, right? And then what will happen if I do this? Well, for opposite, for vectors that are completely opposite, this one minus, and then this will be minus one. That means that it's one plus one, which is two. So the distance, the maximum distance here will be two for vectors that are completely opposite to each other. If this is zero, then the distance is simply one, right? And if this is the similarity is one, which it means that they're collinear, then one minus one equals zero, which is what we want, because when two things are very similar, we want their distance to be zero. So it makes sense in a way that it goes from just, you have to like understand that this goes from 0 to 2 and not from 0 to 1, as it's kind of like the usual more general approach. But this goes from 0 to 2 and that's it. Doesn't matter, right? What matters is that it's low for things that are similar and it's high for things that are different. However, this is not really a distance measure because it breaks both the triangle inequality and the coincidence axioms. Well, the triangle inequality is because you can have, in this case, you can have situations where because the similarity can be negative, it's not, the similarity itself is not shaped in a way that is only positive, then you can have problems where you can take a detour and end up being shorter than the actual direct distance. I'm not going to discuss that in details, but it does happen. And the coincidence axiom also breaks because, again, if you have two vectors which are, one is multiple to the other, their distance will be zero, even though they're not the same vector. You could argue, and that's what they argue in the book, you could argue that, look, at this point, I'm not considering vectors as being, let's say, as having magnitude. So I'm just considering the direction of the vector. So that's fine for the coincidence axiom, because again, of course, if you have two vectors that are, both of them are unitary, so they're unit vectors, which means they have norm equal to one. So then in that case, yeah, the only way to have a distance of zero is if it's the same vector. But again, it depends on the space that you're considering as the input to this. It doesn't really like matter that much. What you can do in order to fix the triangle inequality, not the coincidence, we're going to kind of ignore the coincidence problem for now. We're just going to consider that every vector is unit vector, and I guess it's not a big deal. But in order to fix the triangle inequality, you have to actually turn it into an actual angle between 0 and 100 degrees, right? And for that, you use the inverse of the cosine, which is the arc cosine function. So you take the actual cosine that you got here from this, you apply the inverse of that so that you actually get the angle between the vectors. You know, because you started from the vectors, so you took the dot product divided by the product of the norms, and then that gave you the cosine, but not the angle. Like, you don't really know the angle here, right? All you know is the cosine. So you have to actually go backwards, so to speak, or inverse of the cosine to actually get the angle, and then divided by pi, and then you have something that is between 0 and 180, and that is always positive. And that fixes the triangle inequality, because then in that case you cannot have not have a shortcut, so to speak, where you go through a third. Let's say you have one angle, you have another, or you have one vector and another vector, they have an angle between them, and then you have another vector. If you rotate that vector to one third vector and then rotate that back to the second one, you cannot have that as a smaller vector, as a smaller angle. I mean, this is, sorry, I think I made it more confusing than it actually is. It's just that you cannot have a shortcut with angles. So in that case, it's perfectly fine as a distance measure, as long as you're willing to overlook the coincidence problem, because we're just considering unit vectors for this, right? And then you basically, this is the cosine distance, right? So as we talked, usually this is used for actual text mining. It's the most common application, but there are other applications actually, which people have applied this in different ways. Now we're stepping outside of these Euclidean spaces a little bit. So the spaces where the data points are vectors of real numbers, which is, let's say, the general case for the definition of a vector. And we're starting to think about, well, what if, for example, I have categorical or Boolean features? So my features are not numerical anymore. They're categories. Like, for example, which city do you live in, right? I live in Växjö, I live in Gothenburg, I live in Stockholm. And or which university do you go to? I go to Linnaeus, I go to Lund University, I go to KTH, or something like that. These values of these features, they are values that come from a predefined set of alternatives, right? If you live in a city, there are some cities in Sweden that you can live in. If you are going to university, there are some universities that you can go. It could be all kinds of categorical features. But the important thing here is that they don't have a numerical relationship between them. You can't say Lund is 0 and LNU is 1 and KTH is 2, and then just consider that as a vector and just compute a distance between them like an Euclidean distance, because of course numbers that are closer to each other will end up in a smaller distance, and that doesn't really make much sense for categorical features. The definition of a categorical feature is that they don't have a numerical representation between them. You cannot do numerical operations with them. You cannot do Lund minus Linnaeus University. That makes no sense. So what you can, the only thing that you can actually do with them is to compare them and to say if they're equal or if they're different than each other. So basically that's where the Hamming distance comes in, and the Hamming distance, I represent this as the h here, is basically just the sum of all the components where the two vectors are different. So you get a 1 if they're different, and you get a 0 otherwise. And it doesn't matter how different they are, because there is no concept here of how different they are. They're either the same or different. I mean, of course, if for one feature, for one categorical feature, but if you have data points where you have many categorical features, like for example, I don't know, 10, let's say, then you can actually be different in 10 different ways, right? If I mean, you can either be 0 or 1 in 10 different ways. So the distance here would then be somewhere between 0 because they're completely different. So no categorical value between them is the same. Or 1 or 10, let's say in this case, when you would say, well, all the categorical features for these two vectors are the same. So if they have 10, for example, right? And then there's everything in between from 0 to 10, because all combinations of categorical features could be either the same or different. And basically the distance, the Hamming distance is this. You just sum how many times they're different, how many times they're the same, or how many times they're different actually is the right definition. Because again, we want this to be a distance, right? So we want 0 to be when they are exactly the same, and 10 when they are exactly completely different. And I'm sorry if I think I changed it a little bit when I was first describing it. So I'm sorry. Let me confirm. Let's say reinforce this. It's a distance, right? So it's a Hamming distance. So it's 0 if two vectors are exactly the same, and it's the maximum, or depending on how many features you have, if they're completely different. So we want the distance to be high when they're different, right? And that's why this omega function here that I put here is actually 1 if they are different, right? So then the sum here, the most that you could get here is n, depending on how many categorical features you have. You can also use one-hot encoding, which is one other way to do it in a more like mathematical way. If you want to do it, it's conceptually it's exactly the same, right? If you're just cycling, let's say, through the features and just comparing them and say, well, it's 1 if they're different, it's 0 otherwise, that's perfectly fine. That works. But if you want to have a more like mathematical approach, because I don't know, for example, you're using NumPy and or some kind of library and you have to deal with numbers, then what you can do is use this thing called one-hot encoding. So what is one-hot encoding? Suppose you have a feature like university. Again, university. Which university do you go to? There are a few universities in Sweden. I don't remember how many, like, I don't know, 20 or something. So there are 20, let's say there are 20 different values that could happen in one specific column where you're asking for the person, which university do you go to? And also maybe they say no university, right? So what you could do in order to do this one-hot encoding is to take each of the alternatives of this column and turn them into Boolean features by themselves. So then every university becomes a feature. Then you either go to that university or you don't go to that university. So it's either 0 or 1 and becomes a number in a way. And then, of course, most people only go to one university at a time. So this will be incredibly sparse, right? You will have this, let's say, for example, 20 features, and only one of them is actually going to have a 1, and all the others are going to have zeros. But still, you can then use that as one way to compute the similarity between these vectors in a more like numerical way, if that fits you for some reason. If you're just doing a more algorithmical or programmatic approach, then it doesn't really matter too much. Also, it does matter if you're mixing up categorical features with numerical features. So in that case, you probably want all of them to be numerical, right? And then in this case, when you do this one-hot encoding, then it's almost like every option becomes one feature by itself, which is what happens. But then if you think about them, especially if they're mutually exclusive, which usually they are, then you can think of them as being orthogonal features that are pointing into completely different directions. And then that kind of makes sense that you can actually then compute distances between them. And then, and then we have added distances for strings, which are actually more or less related to Hamming distance, but they are a little bit more complicated. And I just want to start by saying that this is related to your weekly assignment. So I guess it's something that could be interesting to pay a little bit more attention to than usual, because what you're going to do in your weekly assignment is very related to added distances for strings. And yeah, we have already discussed a bit about how to compute distance between text documents, right? Especially when you have a collection of text documents, so you want to compare them to each other, and then you have all these things about the vector space model, term frequency, inverse document frequency, and so on. but we have not considered the distance between the strings themselves, right? There are so many ways of computing this, but the book has one specific way that they talk about, which is this shingle thing where you're breaking the strings into smaller, let's say, substrings and then comparing that. That is perfectly fine. That's one interesting way of doing that. It's related to the vector space model a little bit, uh, other than the fact that the shingles have fixed size. So it's not like a term, it's anything that's between spaces. Anyway, I'm not going to go into that because we're not going to talk about that today. What we're going to talk about is added distances. And the idea of added distances is that you have a string S1 and you have a string S2, and you want to say, okay, is S1 similar to S2? Well, for the added distance perspective, they are similar if you can transform one string into the other with a small number of operations. Operations is a vague term and it's defined differently for different added distances. There are many types of added distances, but the concept is the same. You have two strings and you want to transform one string into the other, right? By doing some operations. And so if you can do that by doing very few operations, that means that their strings are very similar because you were able to go from one to the other, taking like a small number of steps, so to speak. So that means they are similar. And just as a spoiler, that actually ends up being a valid distance measure, which is quite cool. So what are the operations that you're allowed to do? Well, that depends then on the distance measures that you're using, the specific distance measures that you're using. For example, let's take the Hamming distance, which is the one that we already just talked about, right? The Hamming distance can be seen as an added distance that only allows substitution. So what does it mean? Well, you're walking through the strings. Let's say you have two strings, and let's say in this case, because we were talking about the Hamming distance as being this comparison between categorical features, right? So that let's just consider that each let's say letter or each character in a string is a value of a categorical feature. It could be because each letter is like a specific set of characters that you can choose from, right? It's not, you can't just be anything. So you can consider that as being a categorical feature, so to speak, or of one letter. It's either A or B or C or D or E and so on. So then if you compare one by one, then you can say, okay, I want to turn the first string into the second string, and all I can do is just substitute one letter for the other, okay? And then how would you do that? Well, if you go through the first let's say characters of both strings, then you're going to ask yourself, are they the same? Well, yeah, if they're the same, then the cost, so to speak, is zero because they're already the same. I don't have to do anything. I don't actually have to do a substitution in that case, right? And then you go to the next one, and then you say, all right, are they the same? No. Okay, so if they're not the same, then the operation I'm going to perform is that I'm going to substitute the character of the first string by the character in the second string. So then let's say I replace that, and now they're the same, right? Because I basically replaced that. So I add up a cost of 1. And then you keep doing that, and then you can see how this becomes the Hamming distance, because basically you're just comparing the characters and saying, well, if they're the same, then the cost is 0, so I don't have to do anything. And if they're not the same, then the cost is 1, because I have to actually replace one character by the other. And then at the end, the two strings will be the same. Ignoring the fact here that the two strings could be different lengths, but let's not get into that, doesn't matter. If they are, then you just take the smaller one and you add like empty space to fit the same length, for example. And basically empty space will simply be, have to be replaced anyway. So you're just adding some extra cost to that. But that is one added distance where only substitution is allowed. But that's not really it's not really the most common one. The most common one is the Levenshtein distance, and also the longest common subsequence, but they're also very similar. The Levenstein distance allows you to do three things. Either you do a substitution as we saw with the Hamming distance, that could be one option. But you can also delete or insert new characters in specific places in order to try to move from S1 into S2. So exactly which operation do you perform is then the actual question that you have to ask. And that is the hard part, so to speak, of the whole thing, of this whole algorithm for computing distances for strings. But the idea is that of course you can go from one string to the other, and probably you're thinking that, well, I could do many different things. I could actually do substitution, but I could actually do deletion and insertion, and I could actually go from S1 to S2 by performing different types of operations. There's not just one set of operations that will bring S2 into S1 or the other way around. Well, you could, for example, think like this. Well, I could go from any string S1 to S2 by simply deleting all the characters in one string and then adding up again all the characters in the other string. That is one set of operations that would for sure allow me to go from any S1 into any S2. But the amount of operations that you're computing in that case would be very large. It would be basically, let's say, n plus m, considering that you have n characters in the first one and m characters in the second one. So you're performing n deletions and then m insertions, right? That would be perfectly fine, but that cost will be very large. So the idea is that the added distance for a string is actually the minimum amount of operations that you could possibly perform in one string in order to turn that string into the next one. So it is an optimization procedure. That the distance itself, as crazy as it sounds, the distance itself is an optimization procedure, is a minimization procedure. So as soon as you've minimized the number of operations that you could possibly do to go from S1 to S2, that is the added distance, and that is a valid distance measure that respects all the axioms that we defined earlier. You can check it by yourself. I won't talk too much about that because I don't have that much time, but you can verify that in not so hard way. So as I said, the Levenstein distance allows deletion, insertion, and substitution. And then there's the longest common subsequence, or LCS, which allows only insertion and deletion. So basically the difference between them is that in the Levenstein distance, a substitution is more or less the same as a deletion followed by an insertion, right? So if you're actually going to substitute one letter for the other, then it's the same as deleting the original letter and then inserting a new one. So the longest common subsequence usually ends up being more costly, because for every substitution operation in the Levenstein distance, you end up adding actually 2 operations in the LCS, so you get 1 extra cost for that. And but otherwise they're usually more or less equivalent. I'm not saying this from a theoretical point of view, just from practical experience. Let's take a look at an example. This is actually from Wikipedia, because why not? It's a very simple one, a good one, of Levenstein against LCS. So 2 different ways of performing this added or computing this added distance between 2 words. And the words we're using is kitten and sitten versus sitting. So what's the distance? What's the added distance from kitten to sitten, for example? Well, if you calculate the Levenstein distance, then the first operation that you're doing is changing the K to an S. So kitten becomes sitten, which is not a word, but anyway, right? You're just, you substitute S for K, and that has a cost of 1, right? And as you can see, just so you guys keep this in mind, it's kind of like, think of it as having a pointer to these 2 words, right? I have a pointer to the first character and I have a pointer to the second character, and I decided to switch them, right? And then as you go through the words like ITT, they're exactly the same, ITT and ITT, right? So you don't do anything because there's no cost involved. They're exactly the same. There's no operation being done. So you just keep moving your pointer to the next, to the next, to the next, until until you get to the E, right? Because then it's sitten and sittin, right? So you substitute the A for the I, and then sitten becomes sittin. Now you move to the next one, and the next one is an N in both words, right? So N and N. So again, you don't do anything because there's no cost involved, and you're just skipping. And then you got to the end of the word sitten, which used to be kitten, but it's now sitten because we applied 2 substitution operations to it. And all we have to do is do an insertion by inserting a G at the end, and then sitten becomes sitten. And now we have basically moved from kitten to sitten in 3 operations, 2 substitutions and 1 insertion. One thing that you might be asking yourself here is, and which is something that I asked myself when I was learning this, was like, okay, how can I possibly determine which are the operations that are supposed to be done here in order to minimize this, right? Because this seems like a very complicated thing. I mean, I could think of thousands of different operations that could be performed here and still go from kitten to sitten. So how did I decide that I actually had to do this, right? And the answer is, this is an optimization operation, which you should not actually like expect that you will just do it in your head. This is a complicated optimization procedure, which we're going to talk about in the next slide. So don't worry that this is complex, because it actually is complex, and optimization is always complex, right? So this is an optimization operation. You're minimizing this, and this thing that you're seeing here is actually the result of that optimization. So you first optimized it, then you say, okay, now let's look at what happened, and then you get something like this, right? For the LCS distance, it's exactly the same, only each substitution is basically a deletion followed by an insertion. So first I deleted K, then I inserted S, which is the same thing I did here. Then I deleted E, and then I inserted I, which is the same thing that I did here. And then insert G at the end. And you end up with an LCS distance of 5. Levenshtein is more common, usually. I don't think it makes too much of a difference. And which one to use is just added distance. It will end up being more or less equivalent. So now we come to the actual question, right? How to do this? How to find this minimum optimal amount of added operations in order to turn a certain string S1 into another string S2 among the potentially immense amount of different operations that you could do in order to do that. And it's basically the core of this, the answer to this question is in this recursive minimization here. So basically, when you ask, so let's say you have a function called live that returns the Levenshtein distance between 2 strings, right? A and B. Now I'm considering here that A and B are fixed just to minimize the number of parameters that we have here. But of course, if you're computing the distance between two strings, that you have to give them to the function. But let's just say that that was given. So when you ask for the Levenshtein distance between A and B, it's the same as having another function here that takes the pointer to the characters and say, okay, the Levenshtein distance between A and B is the Levenshtein distance between the last character of A. That's why we have length of A here. For example, if A has 10 characters, then this means 10, which is like the 10th character. And length of B here, I don't know if B has 12 characters, then this is the pointing to 12. So that means the 12th character, the last one. This is the answer that you're looking for, the Levenshtein distance between the 2 final characters of each string. Because since this is a recursive operation, the results of the final character will depend on the results of the second to last character. The results of the second to last character will depend on the results of the previous one, and so on and so forth until you get to the actual first one. So the subsequent character always depends on the previous character, and the previous character always depends on the previous character, and so on and so forth until you get the first one. So the first one doesn't depend on anyone because it doesn't have a previous character. So again, asking for the distance between 2 strings is equivalent and to ask the distance between the two strings, given that you're starting from the two last characters, okay, because of this recursive dependency. So I'm going to skip this one for a minute and we'll focus on this other one here. So when I ask for what is the Levenstein distance between the characters I and J, so ith character from A and jth character from B, right? And again, we're starting from the last one, but in general, the recursive definition here is that if you're asked for this one, the Levenstein distance between I and J, that is the minimum of these three operations here. And these three operations here are basically the three operations that we're allowed to do: insertion, deletion, and substitution, or simply skip, right, if they're the same. So why is this like this? Well, it is like this because basically we don't know, right? So if we ask for what is the optimal operation that I should perform in the last two characters of a string, I don't know. It could be an insertion, it could be a deletion, and it could be a substitution. And since we don't know, actually what we're going to do is the simplest thing we could possibly do. We're actually going to try all of them. So basically I'm saying I don't know which one is the best one, insertion, deletion, or substitution. So I'm going to try the three of them. And whichever gives me the minimum cost, that's what this min here is saying. This is the one that I'm going to actually use as the distance. And how do we try all of this? Well, since the results of the last one are based on the previous one and the previous one and so on and so forth, then basically we're saying, okay, for example, this one is equivalent to a deletion. And I'm gonna go through an example of this computation. So maybe, hopefully this will be a little bit clearer later. But this is related to a deletion. So I'm saying, okay, suppose that I delete the current character from string A. That is a cost of 1, okay? So compute the cost of everything else, of the whole thing before I get to this character, and using the full J here. That's why this J, sorry, the full B. That's why J is not changed here, because we still consider the full B since we're only deleting a character from A. And that's why we moved back one character here, I minus 1, right? Because basically on A, we're moving a character back because we're deleting a character, but we're not deleting a character from B, so J stays the same. So basically I'm saying, okay, compute the whole thing, the rest of all the costs that you will have for the rest of the string, add 1, which is the cost of actually doing one deletion here that I just did, and give me some cost. And then I will have some cost here. And then I will save this somewhere. And then the next thing is, okay, suppose that I actually insert a value here. So in a way, I'm saying actually, so I stays the same and J goes back 1. This is a little bit confusing, but it makes sense when you watch the thing happening. It's because in a way you're basically saying, well, suppose that I inserted a character here, and then I moved back. So, but when you move back, you're actually moving back to the same I that you had before, because you added a character and then you move back. So like if you have an A and you add a B, then you jump back to A because you're jumping back. So anyway. This is why I stays the same here, and J goes back 1 because we're moving backwards over the strings, right? Anyway, I'm going to go through an example, and then I guess it will be a little bit more intuitive. But basically, this means a deletion. Just accept the fact that this means a deletion. So a deletion has a cost of 1. So I'm basically saying, okay, suppose that I performed a deletion here. That was a cost of 1. Compute the whole rest of the Levenstein function for the strings that are left here. And then when you give me back that cost, add 1. And then again, let's compare this with this one. And then to try to find out which operation is the best one, because I don't know. So I'm trying everything. And the second one is I actually move back on both strings at the same time. So I minus 1 and J minus 1. Plus 1 if the two characters that I'm pointing to are different, right? Because if they are different, then I have to substitute them. And substitution is one possible operation in the Levenstein distance, right? So again, I don't know, maybe it's better to insert, maybe it's better to delete, or maybe it's better to substitute. We're gonna try all of them. So give one here if I'm substituting. If they're actually the same, then you actually don't get a one here, you get a 0, because there's no cost when two things are the same, right? Two characters are the same. So there's no cost there. So you don't add any cost to it. You simply move back the pointer and compute the rest again in a recursive way. So this is why it's recursive, because we're basically saying the current cost that I have is based on the cost of everything else that came before me. So before I know the cost, you must go and compute everything else. And then you let me know what the cost, and then I will make a decision. And then, of course, when you actually call these recursive functions, they're doing the same that we're doing right here, right? So they're also saying, okay, oh, you want to know the cost of the second to last character? Well, actually, I don't know. So I'm going to try everything again and again and again and again. And this actually branches out in a tree, right? Because every call ends up with 3 extra calls. And then every one of these 3 extra calls also ends up with 3 extra calls, and so on and so forth. So this can be quite a time-consuming process and quite a complicated process. But hopefully when we go through the example, you actually understand what I mean. And I'm going to also introduce you a small trick that you can use in order to fix that, and so that you don't have to worry about actually the time consuming process that this thing is. And okay, so you know what, let's start with the example actually. And I'm going to move here to my other screen where I can actually draw. So we're going to do this with my whiteboard, virtual whiteboard. And basically the 2 strings that we're going to be comparing here are men. So I chose, let's say, 2 small two small strings as an example, so that we don't have to go crazy here too much. So we're gonna compare man and moon, right? There is a set of operations that we can use in order to turn man into moon, right? And we're gonna try to find out which are these operations, like which are the minimum set of operations that we can use in order to turn man into moon. You might be doing it already in your mind, and it shouldn't be so hard to actually find it. Right now, what I'm doing here is I'm adding the actual indexes of the letters so that we can follow them as we go. So we know that, you know, index 1 for the first word, and let's just say that this is like A and this is B, right? So if we have two strings and their names are A and B. So what I'm looking at here, what I want is to have a function called lev, let's say, and then I say, okay, give me the Levenstein distance between A and B. So A and B are 2 strings, right? And I don't know that yet, but that is equivalent, or let's say internally, that is equivalent to calling a certain, let's say, other function here called liv AB 3, 4. And why 3, 4? Because man has 3 characters, moon has 4 characters, and so I'm pointing to the last 2 characters, the third one from string A and the fourth one to string B. And then we start the recursive operations here. So I could say, well, this is the minimum of actual 3 operations that we're going to perform, all of them, and then choose the one that has the minimum cost. So that's the minimum of the Levenstein distance. And guys, I'm not going to be writing all the time AB and AB, AB. So please assume that AB here is fixed, okay? So that is the Levenstein distance between the second character and the fourth character. So this is a deletion, because it's like, think of it as if I had deleted n. So I deleted the character n, And now I'm comparing May, MA with moon. So that's why I'm pointing to 2 and 4. So would that be a good operation? I don't know. Let's try. The second thing that I'm going to try is 3, 3. And again, this is equivalent to an insertion, okay? Because then I'm basically comparing now the N from men to the second O from moon, so men and mu. And that is equivalent to me adding something in this, at this point here, where we were before, right? So let's say, for example, I added something here, and then this would be the fourth character. So then when I moved back one character, then I basically ended up at 3, 3, which kind of sounds like I didn't move anything back because I have the same than before for the first, but I did actually because I added something. And then finally, we have the Levenstein of 2, 3. Oh, let me just write that again. Plus, and then plus here is the question, like, is it +1 or not? Because this third option here is the substitution option, right? So basically I'm moving again back to the previous characters, so 2 and 3, because I'm assuming that I performed the substitution here, but actually I didn't, right? Because the characters 3 and 4, they are the same. So there's no cost in substituting them, so to speak. So the substitution here has 0 cost, and that's the ugliest 0 I've ever done in my life. So this is this cost is 0. Now, okay, this is what it is, right? And I just have to mention something that I actually forgot. Sorry, guys. Because I skipped one part of the recursion here, and the truth is that if we keep going back, actually at some point one of the strings is going to end, right? Like we're gonna be at the first characters of each string, so there's nowhere else to go back to, right? And when that happens, which is what I skipped in the previous formula, when that happens, the cost of that operation is fixed, is set. So you don't have to keep going through the recursion. The cost of the operation is simply the remaining characters of the other string that's not over. So for example, if we reach the beginning of A here, and we still have like 2 characters in B, then the cost is 2, and that's it. Okay. I hope this will be clear as I move on with the operations here. Now, I have to compute these 3 operations, okay? I have to compute the Levenstein of 2, 4, the Levenstein of 3, 3, and the Levenstein of 2, 3. I have to, because I don't know them. And it's part of that is what will give me the solution for 3, 4, and by consequence, the solution for the whole thing. So let's do it and then I will start with 2, 4 simply because it doesn't matter, right? I mean, I could start with any of them because I will have to do all of them anyway. So this becomes then the Levenstein, and I'm going to become a little bit faster here because or else we'll never finish this in time. But basically, if you follow the equation from the slides, you will always get this. And again, here I have to, you can always just like do this very, very quickly because you don't have to keep thinking all the time, oh, is this an insertion or is this a deletion or whatever. You just follow the recursion as it is in the website. And as you can see in the slides, as you can see, it's always like for the first one, I take 1 out of the I. For the second one, I take 1 out of the J. And for the third one, I take 1 out of both of them. So we can just keep going through that a little bit faster. Only that when I get to the substitution, then I have to decide whether I add a cost or not here. And that depends on whether the characters are the same or not. And the characters 2 and 4, in this case here, right? 2 and 4, they are not the same. So it's an A and an N. So I do have a cost here for a substitution. If I decide to substitute one for the other, there's a cost involved, all right? Let me do it like this. No. So great, I have this, but again, I don't know, right? Because it could be one of them. So I'm gonna put here the minimization, right? it's a minimum of these three values. I don't know which one of them is the minimum. So again, unfortunately, I just have to go and compute them. So I'm gonna again start with the first one, because why not? So again, we have a minimization here. Again, we have three computations. And again, we start by taking one out of the J. Then we take one out of the, oh, sorry, take one of the I, and then take one out of the J. And then you take one out of both. And again, I have to decide, are they the same or not? Is there a cost or not? Well, 1 and 4 are not the same, because it's M against an N. So yeah, there's a cost here. And now we got to an interesting situation here. Two of our computations here are straightforward. We don't have to compute them anymore, because in two cases here, the first string has ended, right? You can see that by the 0 that's in this here. If I'm computing the Levenshtein distance between 0 and something, that means that one of the strings has ended. And usually it's the first one, because the first one is smaller, right? So then I don't have to do anything else anymore, because I know the answer to this. And the answer to this is 4, for example, in this case, and 3 in this case. And the reason is, again, because of the one part of the slide that I forgot, I skipped, is that whenever one of the strings are empty, the cost becomes simply the amount of characters that are still remaining in the other string that's not empty. So in this case, there are 4 characters remaining, for example, here in moon. So that becomes 4. And down here in this one, and down here, there are 3 characters remaining, so that becomes a cost of 3. And then, of course, 4 plus 1 equals 5, so I have a cost of 5 here, and 3 plus 1 equals 4, so I have a cost of 4 here. And that's it. Just keep it like saved, because then we are going to have to compute the Levenshtein distance between 1 and 3, because that is not straightforward, right? That one we do have to compute. And we do it, let's say we do it here. So Levenshtein distance between 1 and 3 is, again, a minimization of 3 things, right, as always. So then this is the Levenshtein distance of, so again, I start by taking something out of the I, taking 1 point out of the I, let's say, or 1 character out. Then I take 1 character out of the second one, so that becomes 1, 2. And then I take 2 characters out, or let's say 1 character out of each, so that becomes 0 and 2. And now I have to decide whether they're the same. So the 1 and 3 are not the same, because it's an M against an O, so there is a cost here. And again, I know that this cost is 3, so that becomes 4. I know that this cost is 2, and this becomes 3. And I don't know the cost of Levenshtein 1, 2 here, so I have to actually compute that one. And let's go and do that down here. So that is the minimization of the Levenshtein 0, 2. So I took 1 out of the first string. Now I take 1 out of the second string, and then I take 1 out of both. And again, we know that this is 2, so that becomes 3. I know that this is 1, so that becomes 2. And I don't know the 1, 1, right? So again, I have to compute that. I will try to be more efficient now. So we say that this is the minimization between the Levenshtein. So I take the first one out of the first string, take 1 out of the second string, and take 1 out of both strings. And in this case, I don't have a cost, because the first characters of each string are the same, M and M. So I don't have a cost here, because I'm replacing character with itself. So there's no cost there. And now we got to another interesting place here, so to speak, because I know this, and this is just 0. Because the cost of, like, if one string has ended, the cost is the amount of characters remaining in the next string, but the next string is also empty, so the cost is 0. And 0 plus 0 is 0, so that's the cost. And this is interesting, because then, okay, now I have the 3 values, and now all I have to do is just find the minimum, right? And the minimum actually ends up being, of course, 0, right? So 0 is the minimum. And what does that mean? Well, that means that the Levenstein distance between the first characters in the two strings, so 1 and 1, as is written here, is 0. And that makes sense because M and M, you don't have to do anything with that. That's 0. So now I return 0 to this one here. So now I know this, and this is 0. 0 plus 1 is 1, right? And well, what's the minimum of these three values here? Well, the minimum is 1 because it's 1, 2, 3. So the minimum is 1. And again, I take this and I say, okay, now I know that the Levenstein distance between 1 and 2 is 1. So I come here and I do it 1. And 1 plus 1 equals 2. So the minimum here is 2. So now again, I know that the Levenstein distance between 1 and 3 is 2. So I come here and this is 2. 2 plus 1 is 3. The minimum here is 3. So the Levenstein distance between 1 and 4 is 3. And that means I have a 4 here. Now, there are a couple of interesting things here. I've made it all the way down the recursion tree and then all the way back, and I've managed to compute 1, right? So now I have to do the same for the extra 2 guys that I have, right? The Levenstein distance of 2, 3, and the Levenstein distance between 1 and 3. Actually, no, because we already know the Levenstein distance between 1 and 3. We have already computed it. So I already know this is 2, and I already know that this is 3. And this is something that we call dynamic programming. I'm not going to go into details there, but when you have a problem that you're breaking it down into smaller problems and then computing those smaller, or not smaller, but let's say independent problems, like in this case, we're breaking one problem down into 3 independent problems, right? And when that happens, if you compute them, you have to save their results somewhere else, like make a matrix where you're saving the results, or a dictionary or whatever, where you're saving these results so that if you call this function again with the same parameters, you should be able to recover those values from the matrix or from the dictionary, from whatever you did it, so that you don't have to actually go down the recursion tree all over again. In this case, for example, we actually saved 2 extra calls, right? Because 1, 3 would call 1, 2, 1, 2 would call 1, 1, and 1, 1 would finish. So in this case, we didn't have to call 1, 2, and 1, 1 again because we already know we've computed it before. Why would we compute that all over again? They're independent, right? The results don't affect each other. So I've computed it once. That's it. I need to compute it ever again. So just save the results somewhere else. And in this case, we saved 2 calls, but in actual like larger problems, you will save thousands of calls. Actually, you will go from unfeasible to feasible, or from like centuries to minutes, maybe, or hours. And that's it. Now, okay, but that still leaves the Levenstein distance between 2 and 3, right? And I wish I could just, let's see. Okay, I'm gonna try to use this space efficiently. I hope I can. So that still leaves us with this one that still needs to be computed, right? The Levenstein distance between 2 and 3 here. So we still need to compute that. And well, let's do it. I mean, we're getting the hang of it, so it's not that hard anymore. This is the minimization between, so take 1 out of the first one, take 1 out of the second one, take 1 out of both. And should we have a cost here or not? Let's see, 2, 3, A against O. No, there is a cost here. Or yes, there is a cost here. Now, which one of these we already know? Well, we know 1, 3 for sure. That's 2 because we've computed it before. So dynamic programming. We know 1, 2. That's 1. Again, dynamic programming. And we don't know 2, 2. So let's compute that. So the Levenstein distance between 2 and 2 is the minimization, or the minimum of take 1 out of the first one, take 1 out of the second one, take 1 out of both. And is there a cost? Yes, there's a cost because A and O are not the same. Which ones do we know? We know 1, 2. We know 1, 1, 0. And we don't know 2, 1. So we have to compute that one. We're almost at the end, I promise. So the Levenstein distance between 2 and 1 is the minimum of, so again, take one of the first, take one out of the first one, take one out of the second one, and take one out of both. And that's it. Oh, hey, do we have a cost actually? 2 and 1. Yeah, we do have a cost, A against M, so no problem. But this is easy. We know this one is 0, dynamic programming. We know this one is 2 because this is the let's say the limit of the recursive, right? One of the strings has ended with 0, so now we take the remaining cost. And we know this one is also 1 because of the same thing. One of the strings has ended, so the cost is the number of characters remaining in the next string. So we know here now the result of this is 1. The minimum here is 1. So we come here and replace this with 1. This is 2. This is also 1 because 1 is the minimum here. So I come here and 1, 1 plus 1 is 2. Great. Now the result of this is 2 because there are 2 actually options for 2, but you know, it's 2. Then we go back all the way up to the root here and we say 3. And yeah, that's it. We finished the computation of the Levenstein. Oh, no, sorry. This is the computation of the Levenstein for 2, 4. Yeah, okay. I actually did. Yeah, so sorry, I was saying that I went, before I told you that I went all the way back to the root of the tree, but I didn't actually, right? Because we're still in the 2, 4 here. So the minimum here is 3. Great. So now we have 3. And again, now we're at the top of the hierarchy right here, right? So this is 3 and this is 4. And again, dynamic programming, I know this one is 2. So 2 plus 0 is 2, right? But we still need to compute this one. And let me hope, I don't remember, but I hope this is actually the last one. So the Levenstein distance between 3 and 3 is, again, the minimum of 3 things. This is, take one out of the first one. No, that won't be actually the last one. Take plus 1. Take that one out of the second one. And take one out of both. And are they actually the same? 2 and 2 are not the same, so there's a cost here. I can't click this because yeah, because there's a button here that you can see and I can't click that. So that's, oh my god, I can't draw anything here. So so yeah, we know this one. This one is 2. We don't know this one, and we do know this one, which is 1. Yeah, so then we have to compute the 3, 2, which is actually going to take a couple more steps. But anyway, I will stop here because I think it's too much. This here will take at least 2 more steps. So it's 3, 1 and 3, 0. Oh, actually just 3, 1. So yeah, I will stop here because I hope that you got the idea. Actually, the minimum will be 2 at the end, right? The minimum will be this one. I have it computed here, but anyway, if you go forward, you will be able to compute this more or less easily. But the minimum will be this one because the minimum is 2. You can see here, of course, if you remove A and you add 2, well, if you replace A with O and you add a new O here, you get moon. So obviously it's 2 operations. And what you might be asking yourself is, okay, I know that the minimum is 2. So I know that there are 2 operations, but which are them, right? And the way that you do this is by following the recursion here. For example, so I know that's 2, and 2 is the Levenstein distance between 2 and 3 here, right? So then let's say I go all the way down to 2, 3 here. And then I say, okay, the minimum here is 2. And I here, right? And I have 2 options. So actually these 2 options will generate the same result. So, but you could do either of them. So let's say we go with the substitution, right? So that's 2. And then the substitution is Levenshtein distance between 1 and 2. And then we're all the way here. Now the minimum here is this one. So that is 1, 1, which we are here now. And the minimum here is this one. And that's it. We reached the end of our operation. So what are the operations? Well, the first one here was a substitution, right? So we substituted n for n, so no cost in there, doesn't matter. The second one was also a substitution here. So basically we substituted here A with an O, right? That was the substitution with 2 and 3. So that's the operation for 2 and 3. Then we jumped all the way here, right? And this was the Levenshtein distance between 1 and 1. That was an addition, right? An insertion. So basically we inserted an extra O here. And then we went to the next one here, the Levenshtein distance between 1 and 1, which is a substitution, so to speak. So let me just make this. This is an insertion, and this is a substitution, so to speak. But it's a substitution without a cost because M and M are the same. And then we got our result here, moon, right, with 2 operations. So again, of course, you would have to go on and still compute the rest of there are 2 extra operations that you would need to do with the Levenshtein distance between 3 and 3. But I'm out of space, and I think it's the point has been communicated. I hope so, at least. The important point here, the most important point of everything, actually, is that you must use dynamic programming for this. If you don't use dynamic programming, you will not be able to perform this with reasonably large strings. And you have to for your weekly assignment. So again, dynamic programming. Make sure you save results of the make sure you save the results of the operations that you do so that you can reuse them when some other function calls the same thing again. Okay. And that was it for the Levenshtein distance. Now we're going to talk about other type of data that does not come from Euclidean space. So it's not a high dimensional vector. It's actually about sets. So similarity amongst sets. And the thing is that we usually think about sets as data sets, right? So sets of points, so potentially high dimensional points. But the truth is that a set itself can also be an item in a collection. So you can have a collection of sets where each point in the collection is an actual set of objects. And in that case, we want to be able to compute distance between sets, right? Examples, very similar, simple examples are, for example, an online shopping cart. So for example, different people are shopping in an online website and their cart can be a set of items, right? And the person who has the website may be interested in finding similarities between these people. So let's say the people are the points, but actually they're represented by their shopping carts, right? And the shopping carts are sets of items. And the idea here is that we want the distance between these shopping carts to be larger when these carts have no overlap. So the people are buying completely different things. So if the people are buying completely different things, then we want that distance to be high. But if the people are buying similar things, then we want this similarity to be, well, in this case, we're talking about a similarity. So the similarity should be high, right? And the distance low. So we're going to invert that in a in a second. But for now, we're talking about a similarity. So again, if two shopping carts are similar, then we want the similarity to be high. And if they're completely different, so people are buying completely different things, then the similarity should be low. In the text document, again, we keep coming back to this example of the text documents because they are good examples of these data sets that don't usually come from Euclidean spaces. But you can think of a text document as a set of words, right? If you're not interested in the actual frequency of the words, then you can just say, okay, a text document has some terms, and the similarity between two texts would be then, well, do they have the same terms independently or of what are the frequencies of these terms? Do they have the same terms or not? So if they do, then the similarity will be high. And a common way to compute this similarity is by looking at the intersection, of course, the intersection between the sets, but not the absolute value, the relative value of their intersection. And basically, this is by computing the intersection, so the size of the intersection divided by the size of the union. So the size of the union basically is the amount of different objects that you have when you put all of these two sets together, both of these two sets together, considering the common and the different items. And when you do that, then you have kind of like a total amount of set of items that you can compare with the relative, with the intersections. Then again, you get a relative number instead of just, okay, the intersection is like 3 or 4. Well, is that good or bad? Depends on how many points you have in the set, right? An intersection of 4, if your two sets have a million items together, if they put them together, they have a million different items in them, then an intersection of 4 is meaningless. But again, if you put them together and they have 10 different objects, then a similarity of 4 is basically 40% of similarity, right? And that's exactly the percentage that you're getting from this similarity here. That's why you need to take into account the total number of points that you have in the two sets together before you do that. This is known then as the Jacquard similarity, not distance, right? Similarity, because then the higher it is, the closer these sets are. And they become basically from 0 to 1. So 0 means no overlap. There's no item among the two sets. And 1 basically means the two sets are exactly the same. Because when you put them together in the union, then the union and the intersection are basically the same because they're the same set, right? And then you simply take 1 minus this, and then you have the distance. So it's as simple as that, because since the similarity itself goes from 0 to 1, then if you take 1 minus that, then it goes from 1 to 0. So it simply inverts it, and then it becomes a distance. And there's no real, let's say, secret to that. And as a very short example, you can see here that you have, for example, two sets here, and one of them, the S set has 1, 2, 3, 4, 5 items. The T set has 6 items, but they have 3 items in common. So the actual, when you put all of these together, the whole thing actually becomes then 8 unique items among the two sets. And since the intersection is 3, then the similarity is actually 3 over 8, which is less than half, right? So I don't know what's the percentage the exact percentage here. So, but let's say it's a little bit more than 30%, or maybe around 40%. Then so the distance is exactly 1 minus that, which becomes 5/8. So it makes sense, right? So if you have like around 30% of similarity, or a little bit more than 30% similarity, then you have around, let's say, 70 or 65% dissimilarity, right? The dissimilarity is larger because of that. And this is how you would compute the distances. The most common way of computing distances between sets is the very ubiquitous. It's everywhere, and you can do a lot of interesting things with this. For example, with text. And now we've come to our last example of a distance measure. And again, we're going to talk about a data set that's not Euclidean. So it comes from network. And usually the most common definition of a network distance is shortest paths, right? Because I mean, of course, if you take 2 nodes that are connected by an edge, then the distance is is obvious, right? Because it's defined in the data set itself, the connection between the two nodes. Whether it has a weight or not, if it doesn't have any weight, then you consider it as being 1. And if it has a weight, then you consider it as being whatever the weight is. However, what if I want to know the distance between all nodes in a network, right? So considering that it is connected, consider there is a distance between them and it's not infinite, then I might be interested in say, okay, what is the distance between some node A and some node B, given that they're not directly connected, right? So we try to extract this by looking at the information that we have, right? And we're not anymore extracting this, let's say, subjective or implicit measures that are computed from values that come from the nodes themselves. The nodes themselves, in this case, don't have any value. All that has value is the connections between nodes. So that's where we try to extract then the distance based on the information that we have. And usually the definition is the shortest path. So basically the shortest number of edges, or if in case the graph is undirected, or sorry, unweighted, so that the edges all have 1, then it's the shortest number of edges. But also if the graph is weighted, then what is the shortest sum of this? How can I jump through these nodes and get to the final node by going through the path that minimizes the actual distance that we're taking through these jumps? And by distance, of course, again, I mean the values that are in the edges themselves, right? The edges, sometimes we see the drawing like this and we think of the distance as actually Euclidean distance between the nodes, but that's not what it is. The drawing here makes absolutely no difference as to how you compute the actual distance. The distance comes from the values that you have in the edges here. And they may or may not be this, let's say, similar. Like, for example, there's an edge here with an 8, and there's an edge here with a 5, and another one with a 4, and then a 5, and they kind of look more or less the same. It's almost like an equilateral triangle here. So that's why I say that the drawing is just a visualization that doesn't really matter. What matters is the numbers. And basically, we're gonna then define the shortest path distance. This is there's a very classic algorithm, one of the most classical algorithms in computer science, the Dijkstra algorithm. And I'm not going to go through it in details because I think it's really not that, let's say, the point of the lecture today. The algorithm is here in the slides, and you can read that later, and if you're interested in reproducing it, for example. But instead of me going through the algorithm step by step in details, what I'm going to do is I just took this example from a website. I thought it was simple and good, and I'm going to try to walk through this example with you so that you more or less understand how what procedure is done here in order to actually find the shortest paths in a graph. But the most important thing that you know is that, well, the common distances in a graph are the shortest paths between nodes, right? So the graph on the top left is the full graph with weights on the edges, right? So you can see that, for example, the edge between 0 and 1 has a weight of 4, and the edge between 0 and 7 has a weight of 8, and so on and so forth. So again, this algorithm it considers the shortest path from one node, like a source node, to everyone else in the graph. And if you want to compute from everyone to everyone, then you simply have to repeat the same process for every node in the graph, okay? Because then you will have pairwise distances between everyone to everyone. But in this case, of course, I'm going through a partial example here of starting from one node and then going through almost all the other ones. And because then I will just stop at some point here. So we start with the node 0. So 0 is green here, right? Because that's where you are. And green means that it's visited. So there's the concept, this algorithm has a concept of a visited node and an unvisited or not unvisited nodes, right? In the beginning, all nodes are unvisited, but then you visit, so to speak, the source one because you're starting from it, right? So it's visited. Then you mark it as green, let's say. From 0, you get to know the neighbors, right? So you know that there is a neighbor 1 and you know that there's a neighbor 7. Even though 1 is connected to 7, as you can see, we don't know that because we haven't visited 4 or 8. We only visited 0. So 0 only sees, from the point of view of 0, the only thing that exists is 1 and 7 for now, right? And we know that the distance from 0 to 1 is 4, and the distance from 0 to 7 is 8, because the edge weights here are 4 and 8. Okay, these are not final distances for now. For now, they are tentative distances, so to speak. It's like, okay, if I were to stop now, if I didn't do anything else, this would be the distances. But I still don't know. It could have, there could be some shortcut or something like this. So I don't know. Okay, for now. And then let's say I put this tentative or this temporary distances to 4 and to 1 as being 4 and to 7 as being 8. Okay, and then I just put it somewhere in an array or in a list or something like this, or in a dictionary more commonly. But again, temporary distances, right? So now that I've did this, I mean, I've been through 0. I've let's say I got to know the neighbors, and I attached some temporary distances to them. The next thing that I wanted to have to decide is, what is the next node that I'm going to visit, right? Because basically from 0, I can go either to 1 or 7. So which one? Why would I choose one over the other? Or is it random? It doesn't matter. Actually, it does matter. In order to make sure that we're minimizing the paths, the next step must be towards the minimum. The node with the currently, like all among all nodes, the one that right now, first, of course, the one that I haven't visited yet, because you never visit the same node twice, so you only visit it once. As soon as the node is visited, that's it. But also, you have to take the one with the minimum temporary distance among all of them that you have stored somewhere. And in this case, it's 4, right? Sorry, it's 1 with a distance of 4. So by the time I visit 1 here, I mark it as green, then basically I have found the shortest path between 0 and 1, and that shortest path has a value of 4. Okay, as soon as you visited a node, it becomes green. That's it for that node. You found the shortest path to that node. All the other unvisited nodes, you don't know yet. All their distances are temporary. But as soon as you visit a node, that is final, period. And now from 1, I can find 2 unknown neighbors, right? 2 neighbors that I don't know yet, it's 1 neighbor that I don't know yet, which is number 2 here. And then the distance becomes 12 here. Why? If it was 8 here? Well, because we always must keep in mind that we're looking for the shortest path from 0 to everyone, right? So even though I'm visiting 4 right now, I don't care really about the shortest path between 4 and everyone else. I care about the shortest path between 0 and everyone else. So the distance here becomes 12, because I say, okay, what is the distance between 0 and 2? Well, since I know that the shortest path between 0 and 1 is 4, then after this I move to 2, then basically I'm summing 8 to this path, and that becomes 12, because that's the temporary shortest path between 1 and 2. So basically it's like, what is the shortest path between 0 and 2 if I pass through 1? Well, that is 12, because it's 4 until I get to 1, and then plus 8 becomes 12. But again, this isn't visited, so this is all temporary, right? And okay, I assign this, and then you might be asking yourself, why did I let's say ignore the edge between 1 and 7 here? Because 7 has a temporary, let's say, distance here of 8, right? And when I take 4, which already, 1, which already has a distance of 4, and I add an extra 11 to go from 1 to 7, that becomes 15, right? So 15 is more than 8. So I ignore that because the temporary distance that I have right now, 8, that is better than the new distance that I found by going through 1 and then through 7. That became 15, right? So I ignore that because that is not that doesn't help me in any way. So that's also part of the process. When you let's say you look again at a node, an unvisited node, and you have a new distance, then you have to compare it with the current distance that's already there. So if it's larger, then you simply ignore it. If it's not, if it's actually smaller, if let's say this edge here was like 1, so that it would become 4 plus 1, which is 5. 5 would be less than 8, right? So what you would do then is you would say, okay, actually this is 5 and not 8. And then you would simply scratch this edge here and add a new edge here from 1 to 7, because that would be then the actual shortest path for now, right? Then actually this is going to happen here. So then, okay, I visited 4. I updated all the temporary distances for all the nodes that 4 can actually see. And what's the next one? Should I go to 7 or should I go to 2? Well, actually, you should go to 7 because 7, among all the unknown nodes or unvisited nodes so far, 7 has the one with the smallest distance, which is 8, because this is 12. So this is the one we're visiting now. And then we're going to 7 now. From 7 has 2 new neighbors, 8 and 6. So we add them to the unvisited set of nodes, the red ones. The distance to 8 from 0 is 15, because that's 8 here. Oh, sorry, I said that's the distance from 0 to 8 is 15, because that's basically 0 to 7, which is 8, then 7 to 8, which is plus 7, that becomes 15. And this is 9 because the distance between 7 and 6 is 1. So 8 plus 1 becomes 9. But again, these are temporary, right? And again, of course, this edge here is ignored, not only because it adds a lot of cost, but also because 4 is already visited. 4 is already green, so you don't do anything else with a visited node. If you're walking around and you see a visited node, you just ignore it because it is definitely already optimized. And now we have 3 unvisited nodes, 2, 8, and 6. Which one should we move to? Well, we move to 6 because 6 has the smallest temporary distance so far. So we visit 6 now, it's green. And this is where something interesting happens, because 6 has 2 new neighbors, so to speak, or 2 neighbors, unvisited neighbors, so to speak. So 8 and 5, right? So you can see here 8 and 5. And now 6 has basically like stolen the edge from 7, because the distance to get all the way to 6 is 9, and then 9 plus 6 is 15, right? And 15 is the same as the edge here that we already had before. So when it's like smaller or equal, then you basically update the path by saying, okay, actually, instead of going the old way, you should go the new way, because the new way is either the same or faster. So it's like 6 stole the edge from 7 here into 8. And now the temporary value for 8 is 15, and the temporary value for 5 is 11. And then again, where should be the next one? Well, the next one will be 5. Then you go to 5 and so on and so forth. And as you can see, by the end, when we actually get to the end here, 12 again stole number 8 from 6, because actually if you, or it's not 12, I keep mistaking these numbers, I'm really sorry. Number 2 stole again the neighbor 8 from 6, because actually if you go all the way to 12 and then to 8, you end up having a cost of 14, which is lower than the previous cost of 15. So this is the actual shortest path. And then by the end here, you see that, yeah. So also, I guess number 4 here had, let's say, I don't know which one, I don't know the sequence, but it doesn't matter. What matters is that this would be then finally the shortest paths from one to everyone else. And all of them are now visited because they're all green. And if I wanted to know now, okay, what are the shortest paths from one to everyone else, then I would have to actually start the whole process again from one. Okay, you usually cannot reuse much of these computations from one node to the next, because as you can see, the costs that you have are always considering all the way from the initial node, so 0, 4, 12, and so forth. So it's a little bit harder to it's not really possible to reason about these things. So you can't really reuse much of the computations here. Yeah, and yes, that's it. So that's how you compute the shortest path between one source node and everyone else in a network, and then just repeat that as many times as you need in order to get all of them. And basically that's it, guys, for the lecture on distance measures. I hope it was interesting. I hope I brought some new additions to your tool set of data mining. And thank you for coming all the way here, and thank you for surviving with me this course. And I will expect a short video discussing the weekly assignment that will be published today. And otherwise, I wish you good luck and a great week, and see you soon.